directly going into how to use space data to tackle climate issues. We have our partner, Alice Bourdet, I hope I got that name right, from the UN Office of Outer Space Affairs. She's going to walk us through how an example of how we can use satellite imagery data to tackle flooding. And this year, we have seen floods in all unlikely places of the planet, and definitely here in the US. And these are issues that are becoming more and more common. And like Michelle was also mentioning, that was one of the reasons why the GIS tool was first built. So welcome, Alice. We can't wait to hear from you.
Thank you very much. So I'm sharing my screen right now, because unlike my colleague Jorge, I don't have it summarized on my t-shirt. Hello, everyone. Good morning, good afternoon. I hope you can see my slides. My name is Alice Bourdet, and I'm working for the United Nations Office for Outer Space Affairs. My talk today is about showing you how you could use space technologies to tackle problems in your community. And it is meant to show you practical and simple examples on how you can use space technologies. So during this talk, I will use several scientific simplifications which work for the general cases and for the uses we will discover today. But first of all, I'd like to tell you a little bit more about the UN Office for Outer Space Affairs before getting into the core of the subject. So the UN Office for Outer Space Affairs has a mission to bring the benefits to space to humanity through promoting international cooperation in the use of outer space to achieve the Sustainable Development Goals. And under this office, there are several initiatives and programs. And just to name a few examples, for instance, on the left side of your screen, you can see a picture of the launch of the first ever satellite from Guatemala, which has been thoroughly supported by UNUSA through the Access to Space for All initiative. And this satellite was deployed from the International Space Station in April 2020. And space can also be used for disaster management, and the UN Spider program, for which I'm currently working, is actually ensuring that all countries have access to and that they can develop the capacity to use all types of space-based information to support the full disaster management cycle. Indeed, space technologies are very, very useful in disaster management, as there are plenty of satellites constantly monitoring different parts of our planet, and a lot of information can be used for it. So I invite you to go and visit the Spider Knowledge Portal to find out what are all those information and what for they are useful. And the link will be given at the end of this presentation. So now let's get started with the core of our topic. So what is remote sensing? So basically, first of all, if you are reading this, you are currently remote sensing. Because remote sensing is the process of detecting physical characteristics at a distance. And the sensors can be various, such as, for instance, when you are remote sensing, you can use your ears, your eyes, and your nose to detect physical characteristics from distance, but it can also be a sensor on an airplane, or also a sensor on a satellite. And there are two types of remote sensing, what we call passive remote sensing and what we call active remote sensing. So the main characteristic of passive remote sensing is that let's take it that it's a satellite remote sensing, then the satellite is measuring the reflected sunlight on a certain surface, on the surface you want to detect. Whereas for active remote sensing, the source of energy or radiation is the satellite, which emits some pulses of electromagnetic waves and measures the reflected wave once it has been reflected by the surface. So here I would ask you a little question. So knowing that passive remote sensing so it's based on sunlight, and therefore the sunlight cannot go through clouds, as you can see with your own eyes. Whereas active remote sensing is able to view and penetrate through clouds. So that's one of the biggest difference of those two types of remote sensing. So according to you, if you want to monitor a place where it's currently raining, I would like to ask you, what type of remote sensing would you use? I'll give you a couple of seconds before answering that. So I guess you now all came up with an answer. You can use the chat function if you want to share your answer. So if you want to see a place where it's raining, you would need to use active remote sensing, because it's most likely, I mean, it's obvious that if it's raining, there are some clouds, and you would not be able to see anything using passive remote sensing. And another advantage of using active remote sensing is that because it doesn't depend on the sunlight, it can also monitor some surfaces at night. It's a all-weather and all-time sensor. So that's for the biggest difference between passive and active remote sensing. So what do we sense using remote sensing? So if we consider that the sensors would be, for instance, the eye of a human, we would sense some radiation within the visible spectrum, so which goes from the blue color to the red color. However, the sensors that we use in remote sensing, the passive and active sensor, can also detect some radiation within the infrared spectrum or even the microwave spectrum. So the microwave spectrum would be only for active remote sensing, when the infrared and visible would be for passive remote sensing. But then when you want to display the results of a sensor, there's one thing to know, is that the screen of your computer can only represent combination of red, green, and blue. So it's from the visible. And indeed, each band, so what we call a band is the range of the radiation that the sensor is able to detect. And each band from that is sensed is normally represented as a black and white images. So let's take an example of red, green, blue images. So as I just mentioned, each image of the sensor is actually composed of it's a combination of 3 grayscale images, and one which will go to the red, like let's call it a red layer, one which will go to the green layer, and one which will go to the blue layer, to be then composed into a single image. So here we take the example of a real color image. You can see that it can be decomposed in 3 grayscale images. So the image which is on the red channel, on this image, you see that the sky appears very dark, because actually there's not really some red in the sky, in the color of the sky. The grass also appears very dark, again, because there's not much red in it. I forgot to mention to you that in each of the grayscale image, actually, the more reflection the sensor gets, the more green will be the pixel. Basically, if the result appears black, it means that there's no response in the surface detected, and the whiter it is, it means that there is a high response. Therefore, we see that in the red image, there is not much response in the sky that is blue and in the grass that is green. But we can see some pixels are white in the, let's say, in the cloud areas, because it's a mix of the 3 colors. Let's look now at the green image. We see on this grayscale image that the grass appears much brighter than in the red image. The sky also is a little bit more clear. That is actually not pure blue, but contain a little bit of green. And finally, the blue image shows that the sky appears very bright, which makes sense because the sky is in the majority composed by blue. But the grass appears black as there's no blue in the grass. And that's by combining the three grayscale images into the right color that we obtain, or what we call true color images, which is equivalent to what we would see with our own eyes. But we can also, so we can either choose to see the remote sensing images in true color, as I just explained, but we can also tell the computer to organize the color layers differently. That's also a possibility because it's all digital processing. So for instance, what if instead of, as you see on the left of your screen, what if we decide to set the green component into the red channel, and then we would put the blue component into the green channel. So if we put the blue component into the green channel, then that's expected that the sky would appear green, right? Like, as you can see on the right. And then we decided to put the red component into the blue. And therefore, now the grass appears red because the green component has been set to the red channel of the image. So that's an example of how we can play with the bands of the remote sensing bands to have different results and to enhance or not visualizations. So in here, I would ask you again to think a little bit about what I said. So let's look at the image on the left. It's a red, green, blue image. And what I would like you to think about is to match the bands with the colors. So basically, which of the black and white image correspond to the red, to the green, and to the blue band? And I'm going to give you a couple of seconds, perhaps 1 minute, to think about it. And if you want to share your answers in the chat, please feel free to, before I give them away. So let's start. I hope you all had results by now, and let's start with the, let's say, the easiest. So on the true color image, you see that the flower appears red. So what you want to do is to find the black and white image that has the highest response in the red, and the highest response would be seen as white. Therefore, the bottom image is the red channel. Then, using the same way of thinking, you want to find, you see that the vegetation appears green, and then you want to find which of the black and white image has the feature of vegetation in the lightest. And then you see that it's the top image. And you can check that the middle image is indeed the blue one, because there are some little stains on the butterfly that are blue, and those same stains appear very white in the blue image. So that's for the visible part of the spectrum that can be used in remote sensing. But there are other parts of the spectrum that we can detect in remote sensing, but only the visible is detectable by human eyes. So of course we cannot see for instance, the near infrared, the shortwave infrared, nor the thermal infrared. But it doesn't really matter because we can tell the computer to put those bands into either one of the channels, and then so that would enable us to see them through a colored layer. So on this graph, you can see what is called the spectral reflectance of 3 different types of surface: the soil, the green vegetation, and the water. And for instance, let's take the example of the green vegetation. So you can see here on the left of the graph that in the visible, so in the blue, it has an increasing reflectance, and then pretty stable in the green, and then after the red color, it increases a lot, and it's very high. The reflectance of the green vegetation is really high in the near infrared, before decreasing a little bit more and being, let's say, unconstant in the mid infrared. And that's what we call, the spectral signature or spectral reflectance of a certain surface. So, quick question for you now. What is the reflectance of water in the near infrared? What can you tell me about it? So as you can see in this graph, the reflectance of water in the near infrared is zero. There's no reflectance, because actually the water absorbs the whole near infrared radiation. And that's a very useful feature, for instance, because if you want to sense that the surface is water, you can use near infrared. And if you have no detection, no return, that would mean it's water. Or for instance, the near infrared is very useful to detect vegetation due to the very high response that vegetation sends in the near infrared. So in this example, you can see the same picture taken at the same spots. The left one is in true color, and the right one is actually, so in the red channel, it's the grayscale image of the near infrared that has been put. And then the green channel, it's the red one, and in the blue, the green. And then you can see that there is a very, very high, or like many pixels are red. And this is due to the fact that the red channel has been set to the near infrared. And as we just saw, the green, the vegetation, especially when it's very green, has a very, very strong return in the near infrared. So this other visualization, the fact to play with the different bands, really enhance visualizations, and it's very useful according to what you want to detect. Here is another example. On the left, you have the red, green, blue channels that have been composed or organized. And on the right, you can see that on the red channel, it's actually the thermal infrared that has been set. And instead of just seeing, like, for instance, the smoke during a fire, you can really detect the area of where it has been burned. And just for you to know, I picked one example of the Landsat 8 satellite, which actually has 11 different bands that you can use and composed different and pick 3 and compose different images. That makes you 11 ways to see the world through those 11 bands according to what you want to detect. So now I would like to show you how all of this can be used through the application of change detection. Change detection is by definition change is by definition the conversion of the landscape from one dominant feature to another. And it can be used using several satellite images, for instance, to detect landslides or agricultural monitoring or urban growth. And basically it can, all the following questions can be answered by satellite image, such as when and where the change has happened, how much it has changed, and what kind of change is it. So here is the example of the Aral Lake. On the left image, which dates from 1990s, you can see the whole extent of the lake as it used to be. And on the right image, it's the exact same place, but taken in 2018. So these 2 images allows you to make the difference between those years and to determine the area of the lake that has decreased and during what time frame it has happened. Another example, which has a shorter time frame, it's more abrupt, is this one. You see on the left that it's pretty much some vegetation with the river flowing like let's say in diagonal of the image. And 1 year later, you can detect the presence of a bigger feature, which actually is a landslide. And you can see that the landslide has started to act sort of like a dam, and that the water is packing up a little bit on the right image. And that allows you to detect, so first this landslide, and to know when approximately it has happened, how much of is the surface of this landslide, and also assess other consequences. This is rather a seasonal change example, and you can see on the left, on the picture taken in April 2018, the different fields and how the land is used. And you can see that a couple of months later, in August, that the state of the vegetation has drastically changed. And finally, the last example of change detection that can be made using satellite imagery is this long-term change of urban growth. You can see the difference in the extent of a city in 1996, sorry, and how it is, or how it was in 2010. So just to recap a little bit, one of the application, a very useful application of remote sensing is change detection. And that can be either landslide, agricultural monitoring, urban growth. And really, yeah, it can answer all those questions that we mentioned earlier.
Alice, do you think we can quickly go through some of the last slides? Because we're a little bit over time. Sorry,
okay.
I know.
Sorry, that's fine. Then I skip this one, and let's move on to the really practical application that I will present you today. So it's how you could map some flood extents using Google Earth Engine. So very quick question. If you want to detect flood, what would you use? Passive or active remote sensing? Provided that it's most likely that if it's flooding, it's been raining a lot, and then you might want to prefer active remote sensing. So active remote sensing, to remind you, it means that the satellite itself emits some electromagnetic waves and measures what's reflected. And usually, indeed, we detect flood using radar satellites because they can penetrate clouds. But another feature, very interesting feature of a radar satellite is that the water appears as a dark feature in radar images most of the time. So that's also very useful to be able to detect water extent. And radar images only have one spectral band, not like the other example I showed you with red, green, and blue. But there are other parameters you can play with, such as polarization, to have differentiated images. And so the practical example I'm going to talk to you today, it's one of our recommended practice that we have available on our website, and I really strongly encourage you to go there and have a look at this one and the other one. So what you need to map the extent of a flood is just a Google account to be able to use Google Earth Engine. So once you open Google Earth Engine, you will have this window, and the code needs to be where there is this orange rectangle, so you can either click straight on the link or copy paste the code here. So once you have the code here, you need to set, the code is already written, and you need only to set 3 variables. So the geometry of the area you want to detect a flood, and it can be either by entering coordinates, or there is also a polygon function where you can just decide where you want to have a look. You need to enter the dates before the flood, where you want to gather imagery to be compared with, and the dates during or after the flood, like when you want to detect whether there's a flood or not. And so that you will be able to perform change detection. And once you have set up, you can also play with the polarization variable to have different results. And once you have entered all the parameter, you need to run the codes. And the code is very well commented. So if you have any doubts or whatever, you can read through it and you will get all the information you need. And once you run the code usually takes 1 or 2 minutes, then you have the result of the potentially flooded area that appears in blue. And this layer is also intersected with different data layers, such as an estimation of the population density, or also cropland or urban areas. And then by intersecting the flood extent with those layers, you can extrapolate, for instance, an estimated number of exposed people by this flood, or the estimated affected cropland, or also estimated affected areas. So, and there are even way more data layers available in Google Earth Engine. So you can even own this code and modify it if you feel comfortable with using Python, and really improve this code and tailor it to your needs and what you feel like. So once again, you will have the links of this code when the presentation will be displayed. And finally, I would like to conclude with this, that perhaps another idea on how you can contribute is that usually flood detection in cities is not very good, due to the fact that the radar signal might have sometimes multiple reflections in building. And so what if the satellite information could be augmented with crowdsourcing? And for instance, geotagged pictures of flood would be very useful and definitely would help improving the detection methods in the future. So that's something for you to think about if you want to contribute. And at the end of the slide on my presentation, I will go very quickly. You can find some data sources and other very useful links if you want to learn more. So I thank you for your attention. Sorry if I took a little bit longer.
Thank you, Alice. I think, yeah, flood detection and is a big thing for us. And so thank you for showing that this is where we can contribute, where a mobile app and crowdsourcing this information can actually help build these data sets even better.